Okay, in this video we are going to use the kinematics of rotation. So it involves angular speed and angular acceleration. And so with that, keep in mind whenever we're dealing with the changes of angles that we need to be in radians. So whenever you're using a kinematics equation, of rotation, you need to make sure that you are in radians. So if you remember, our kinematic equations from before were there was 4 of them that we tended to use, and this could be revamped into different ways, or rearranged, but there was 4 of them that we tended to use most often. And then so those are our kinematic equations. Now for rotational, remember, instead of dealing with how far something traveled in the x direction, we're going to be talking about how many angles or radians it traveled, and how far it went in a certain amount of time. So we can really just transfer, if we think of x equaling theta and omega, let's keep it consistent here, and v equaling omega, because that is angular speed, and then a equaling alpha, which is angular acceleration. We can just rewrite the equations for kinematics of rotation as theta equals omega times t. We have omega equals omega initial plus alpha times t. We have theta equals omega initial times t plus 1/2 alpha times t squared. And then we have omega squared equals omega initial squared plus 2 alpha theta. Okay? So just like with the original kinematic equation problems, when you're using them, I suggest that you identify the information given to you and what they're asking you to find, and then pick out the formula that works best. So with that said, I'm going to erase these original kinematic equations so that we can have space to make our list and then identify which one of our equations fits our problem the best. Okay, so if I look and I read this, it says the blades of an electric blender are whirling with an angular velocity of, so we have omega initial equals 375 radians per second, while the puree button is pushed in. When the blend button is pressed, the blades accelerate and reach a greater velocity after the blades have rotated through an angular displacement of, so theta equals 44 radians. And then the angular acceleration is 1,740 radians per second squared, and we're looking for our final angular velocity. So we do not have time, so we don't want to use this one here because that involves time. We don't want to use this, that involves time, and we don't want to use that. So we're stuck using this one right here. Okay, so I'm going to erase some of this so that we can have space, and then we want to solve for our final angular speed. Okay. So I'm going to just plug in some of our numbers here. That's what we want to find. 375 radians per second squared plus 2 times 1,740 radians per second squared. And then theta is 44 radians. So when I've plugged that all in, I'm going to take the square root of my answer. Let's see, 375 plus 2 times 1,740 times 44. We're going to keep 2 sig figs in our answer. Or no, sorry, 3 sig figs in our answer. And we end up with 5 omega equals 542. And since it's omega, the unit is radians per second. So kinematic equations of rotation is very much the same as kinematics of linear movement.